Good afternoon. For first 2-3 meetings, we are focusing on the boundary value problems. That is one of the approach to calculate electric field or potential. If the, or sorry, it's one of the approach to calculate. It's electric field or potential. If the source details were available only on the boundary, if the details of the charges or potential is not available on the entire region, then you can go with the boundary value problems and you can solve by using the Laplace equation or Poisson's equation. Other approach as usual, Coulomb's law and Gauss's law. Then you can use scalar electric potential. So those three methods you can use if the details are available in the entire region. If only at the boundary the details are available, then you can go with this fourth option. We can consider it as a fourth option, where we can calculate electric field or potential. Also, you can calculate capacitance, resistance, everything you can calculate. Ultimately, you need to find potential, then you need to find electric field. From that, you can calculate capacitance or resistance, anything you can calculate. So that's what the fourth module as per your fourth or third, I don't remember. I think fourth module as per your syllabus. Title of the module is boundary value problems. In continuation to that, there is one more topic called method of images. This is, you can say, even the fifth method to calculate electric field. But it's not applicable to all problems, but it's restricted to some problems where some infinite a metal plane or a metal is exist and above which some charges is present. And if you are asked to calculate what is the electric field or potential, then you can use this method called method of images. So it's now let us look at this. So in the method of images, first understand this point. It's used to find, you can say it's a fifth method to calculate electric field or potential. Okay, so first method is Coulomb's law, second is Gauss's law, then we use electrostatic potential, then fourth is boundary value problem where Laplace and Poisson's we have used, and this we can call it as, you can consider it as a fifth one, which is the method of images. So in the method of images, this is applicable when there is infinite metal plane exists. So this is metal, or we can say it is a equipotential body. So above which some charge is present. Let us say Q, a point charge, or it can be a line charge, or it can be a volume charge. It can be anything. Okay? Or it can be even sheet charge, or it can be a volume charge. If due to this system, let us say above metal, you have this point charge, line charge, surface charge, and volume charge. So such charge systems present. What is the potential, or what is the capacitance, what is the electric field? If you are asked to calculate all those things, you can use this shortcut method called method of images. Still, you can use other method. You can use the boundary value problem where you can apply the Laplace and Poisson's equation. But compared to that approach, this method of approach is quite easy. See, what we will do is, we will replace this metal plane. Let us say this is the infinite metal, bottom side is infinite metal, and above which you have a positive charge or some charges is present. So what we will do is, we will replace this infinite metal body with equipotential plane. So equipotential plane is a plane where potential is 0. And as usual, this positive charge is there. And let us say the height of the positive charge is h. Sorry, the positive charge is kept at the height h above this metal. Now what you need to do is, keep the positive charge as it is at height h above the equipotential plane, and now you create an image. Image is like a mirror image. So if you take a mirror image, it will be a negative to that, right? So it will be a negative charge. Okay, so this positive charge above a metal plane equal to a positive charge and its mirror with respect to the reference plane, or you can say it's equipotential plane. Then we can easily solve this problem. Now we can see we have eliminated the metal part. Now we have only two charges. Early we have only one charge, but some metal was there. So if you want to solve this problem, you need to apply the boundary condition. But in this case, you can avoid that such cases like boundary conditions. Such complications you can avoid. Okay. Now we are going to prove that. First, we will see a small derivation, and we will understand this replacement of this metal with this image charge will yield in the same result. First, we will see that. Then we will look at one example. So it's a simple topic. Even we can't expect a 10-mark question. It's going to be very simple topic. Okay. Here we have considered a point charge. Instead of point charge, you can, if it is a line charge, let us look at this picture. Point charge, if it is positive charge, you can see it is replaced with a negative charge. If it is a line charge, it's replaced with a, see, if it is positive line charge, it's replaced with a negative line charge. Thing is, you need to change the sign. Change, take mirror or take an image, reverse the sign, replace this metal, and that meeting boundary is there, right? So this meeting boundary should be replaced with equipotential surface V equal to 0. This is known as the image method of images or image theory. So read this. This is the definition. The image theory states that for a given charge configuration above infinite grounded perfect conducting plane may be replaced by the charge configuration itself, charge configuration itself, its image, this image, and an equipotential surface in place of the conducting plane. Now let us prove that by replacing this the charge above this infinite conducting system is equal to image of the charge and equipotential plane. Let us prove that. Now for that, consider this picture where a positive charge kept at a height h above this infinite metal body at a height h, and this metal body V should be 0. It's equipotential body. Assume it's at 0 potential, V equal to 0. Now it's replaced. Now you can see it is replaced. You can see this is a positive charge, and at same height h below, a image is created. So this is image, and this metal is replaced with equipotential plane V equal to 0. Now let us solve the problem. So plus q minus q equal height above and below this reference plane. Now let us first calculate the electric field. Now assume this point, observation point P, where P equal to x comma y comma z. So at this point we want to calculate the total electric field. So total electric field equal to, now consider this picture, image picture. Now it's easy, right? Now we don't need to bother about this metal, all this stuff. Only thing is two charges. So electric field total at the point P x comma y comma z is equal to electric field due to this point charge and electric field due to negative charge. So the formula for electric field due to a positive point charge is q upon, so it's positive charge, right? Q upon 4 pi epsilon, maybe epsilon or epsilon naught, anything you can take, epsilon r vector over r cube, right? R vector over r cube, or you can take ar vector or unit vector over its square, right? R square, so anything you can take, plus due to the negative charge minus q over 4 pi epsilon. See, there are now two charges, right? Q1, Q2. Q positive charge and this is negative charge. So distance, the vector connecting the positive charge and the point P is, let us take R1 vector and this is R2 vector. Okay, so now let us replace this to R1. Now the distance between the negative charge and the observation point is R2 over 4 pi epsilon R2 raised to 3. This clear? Now let us write the equation for R1 vector. So R1 vector is the endpoint minus starting point, right? Or the field point minus the source point. The field point is x, y, z. Where is the source? Source x, y I have not defined. Assume that x is at 0, y is at 0, z is at h, 0, 0, h. So this point is at 0, 0, h. So it is along the z axis. So it is along the z axis. So R2 vector, sorry, R2 vector equal to xyz minus 0, 0, minus h. So this is at 0, 0, minus h. This is at 0, 0, plus h. That's all. Now we can put all those things. Is it clear? Now if you plug this condition, vector and magnitude, if you replace, then you will get this equation. So this q upon 4 pi epsilon naught will be a common term. You can take this outside. So rest and see this equation. Now you can see it is a function of x, z, y, and z. So electric field may be along the x direction, also along the y direction, also along the z direction. That's one point to observe. Otherwise, this lengthy equation really won't help us. We won't use this in the future. So leave it. But one important point to observe here is if you put z equal to 0, what happen? If you put z equal to 0, if you go to put z equal to 0, this will be 0, this will be 0, right? And this minus is it equal to 0, what happened? So both will be 0, right? So what will happen? You can see this two terms are equal, right? This along x and y it is equal. See, first understand the denominator is equal. So now numerator, let's consider one component after other. Now if you take x into ax, you can see both are equal, right? So there is a minus sign. So x term will get cancelled. Same way y term will also get cancelled. There will be no field component along y direction, but only there will be field at z equal to 0. You put z equal to 0, the electric field will be equal to q upon 4 pi epsilon naught. So if you put 0 here, it will be minus h into a z upon the denominator term, minus here if you put 0, it will be h into a z. So other terms vanished, that is along x, y, both are vanished. Okay. So the point here is at z equal to 0, this is the corresponding to z equal to 0, right? At z equal to 0, electric field is only in this direction. So you can see in even this picture, electric field is only perpendicular to the boundary, not you can say z plane. Electric field is perpendicular to the z plane. It is not tangential or it is not along. See here it is bent, but here you can see it is straight. It's perpendicular, normal to the boundary. The reason, hope you understand, this plus q and minus q are symmetry with respect to this z equal to 0. That's why. This point is clear. When z equal to 0, electric field will have only z component. Based on this, you may get one quiz question. Next. Now electric field here calculated. So likewise, let us calculate potential and other possible things. Let us calculate. Now let us calculate potential. So potential, total potential is potential due to this point charge and potential due to this negative charge. If you recall the formula due to the potential due to a point charge, it is q upon 4 pi epsilon naught, epsilon into r. Right? So it is r1. Same way for the negative charge, it is 4 pi epsilon r2. That's all. So this is a formula we already had, right? For a point charge, potential due to point charge. If it is brought from infinity, this will be the potential at some point. Now you know R1 and R2 previous we have calculated magnitude of R1 and that's magnitude of R2. You can plug it and so it's a scalar. Now, so potential is calculated. Now let us calculate the charge density. So electric field has calculated, potential we have calculated. Now let us calculate the charge density. The reason for calculating the charge density is more practical here. There is some practical reason. Even you had already some topics like this. Like if you bring a positive charge here, what will happen? Equal and see a negative charge will be induced here, right? So plus the electric field lines will go like this, right? Okay, so the amount of charge induced will be minus q. Now we want to see what is the charge induced at z equal to 0, or then this metal, how much is the charge induced? That's what you want to check. So rho s you have to calculate. That is the charge density, because below which you have a metal thing, and you want to calculate rho s charge density. Okay, so you can calculate the charge density using this formula: ds equal to rho s equal to dn. Okay, so if you find the electric flux which is normal to the boundary, you can able to say what is the rho s here. So what is the surface charge density? So this is from the dielectric metal boundary condition. Even last class we have used this boundary condition. So keep this boundary condition frequently. We will use this boundary condition. Electric flux normal to the boundary will be equal to the surface charge on the boundary. Now you need to calculate dN, that is electric flux normal. You know, D equal to epsilon E. So D equal to epsilon E vector equation is here already, right? So you can write the equation. Maybe you can write this lengthy equation. But the point here is normal component. We want to find only the normal component, En, right? So dN equal to epsilon into En. What is the normal component? Let us say this is equation A. You consider equation A. From equation A, what will be the normal component? It will be Q upon, I think previous slide itself we have calculated, right? What is the normal component? If you take this first term, the normal component is, what is the normal component? The normal component is a component along Z direction, right? So this is Z direction. This is X, this is Y, and this is Z. So we don't want these two components. That's all. So when you will get when you can able to get this normal component alone, so that's possible only if you put Z equal to 0. So if you put Z equal to 0, so you would get minus h upon, I think previous slide we have discussed this. So this will be the normal component. So normal component is it's perpendicular to this metal plane, or V equal to 0 plane. So if we put it will be minus 2h in the numerator, right? So let me write directly here 4 pi epsilon naught. So here it is minus 2h, sorry, minus h into AEZ minus h into AEZ upon this denominator term. So this will be Q2h upon 4 pi epsilon naught in the denominator term. So this 2, 4 will get cancelled. You will get minus Q h multiplied so it's along the z direction over 2 phi epsilon naught. Sorry, epsilon will not come, right? Because we are calculating the d, right? So epsilon term will not be there. Then denominator term. That's all. That's what. Okay. By forcing z equal to 0, or by finding the normal component, you can get that. Or by considering only the AZ component, you can find this. Is this clear? While solving the problem, this is a critical point. Z equal to 0, or the normal, finding the normal component is an important point. Shortly, we are going to practice one problem. So far, electric field is calculated, potential is calculated from the basic simple formulas. Then we have calculated the surface charge density using this boundary condition. Then fourth, let us calculate, as we know, this rho s. we can calculate the total charge. So rho s is known, right? Surface charge density is known. Now we want to know what is the total charge. See, the point is, like, this is the boundary, this is a plus q, this is minus q. Now we have calculated rho s equal to some equation, some big equation, right? Some big equation. So minus qh upon 2 pi some length equation. Okay, so this is what the surface charge density. Now we need to calculate the total charge. Okay, what is the total charge? Don't put total, charge induced. Because if you bring a positive charge close to a metal body, it will induce a equal and opposite charge on the metal body. Now we want to calculate what is the total amount of charge induced. So we can use this formula, Q equal to rho s into ds. So rho s is the surface charge density induced by this positive charge. Okay, so from the surface charge density, you can calculate the total charge. So rho s we have calculated in the previous slide. Now we need to find ds. What is ds? ds surface area is dx into dy. So this is x, sorry, this is y and this is x. So dx into dy. And dx dy, what is the integral limit? What is the integral limit? It is infinite, right? So minus infinity to plus infinity, x equal to minus infinity to plus infinity. Then you can solve the problem. Now, as we can see, this is infinite. Whenever we get into infinite, we try to apply the cylindrical coordinate system rather than the Cartesian. Then equation will be reduced and you will get a simple, nice equation. That's what we will do now. Any of this derivation is not important. See, this is what until this step I have shown earlier, right? Now express this this first equation in cylindrical coordinate system. So cylindrical coordinate system, see, what is x square plus y square equal to rho, right? Rho equal to square root of x square plus y square. So this is rho, this is, say, this is x, this is y. So rho equal to square root of x square plus y square. Okay, so replace this x square plus y square with rho square. Point number 1, right? Remaining rest as it is, right? So I will write it again. So x from minus infinity to plus infinity, and minus y is from minus infinity to plus infinity. This is what's in the Cartesian coordinate system. Now we have converted into cylindrical coordinate system. If you take the cylindrical coordinate system, it will be rho and phi. So radius will be from 0 to infinity and phi will be from 0 to 2 pi. So inside, what you need to do is you replace x square plus y square with rho square. That's all. And you need to replace dx into dy with the surface equation for the cylinder. 3 possible surfaces are there. You need to take the surface which is normal to the z direction. So the surface is d rho into d phi, which is perpendicular to z direction. So you need to replace dx into dy with rho into d phi. That's all. Okay, if you do that, I will get the total charge induced equal to minus q. This already we know, right? This is a positive charge is brought close to that infinite metal body, then it will induce the equal and opposite charge. Just we got it. Now, what really we have proved is the point is like infinite metal above which there is a positive charge. We are replacing it with the same positive charge, and we are replacing this equipotential plane, a body with equipotential plane, then put a other charge at a distance equal but on the opposite side, and the charge should be opposite. Okay, so already we know that the here the charge induced will be minus q, and even with this approach, mathematically we have proved that charge induced will be equal to minus q. Any questions? maybe a lot of equation might be there in this slide and simple, but this equation is really not required. Directly you can solve the problem, so don't worry about this. You don't need any of this equation. Only the approach is sufficient to solve any problem. Now let us try one problem, then we will understand. Forward one image. You will get one question, maybe a 5-mark question. In the CAT or in the FAT also, you will get one question from this. So please try this. So I will give off many time. First, realize what is the given charge system is. Charge system and how the problem will look like. You can draw a picture and you can understand. Let me explain. So there is a conducting plane at z equal to 0, and there is an infinite line charge 16 nanocoulomb rho L equal to 16 nanocoulomb per meter is located in free space above the conducting plane. So where is the location? What is the location of the infinite line charge? It is let us not properly align to the coordinate system, but anyhow let us at least fix x, y, z. Now where is that infinite line charge? Where is that infinite line kept? X equal to 3, y is from minus infinity to plus infinity, z equal to 4. So that it will be how it will look like. It will be along the y-axis, right? So something like this. Okay, so infinite line charge rho L at 3 comma y comma 4. This is important. Y is y because that is from minus infinity to plus infinity, right? And the value is 16 nanocoulomb per meter. So it is surface, not sorry, it's a line charge density. It is given. Now you need to find as usual, like two things like electric field and induced surface charge. So first step, now let us apply the image theory. So replace this infinite conducting plane with equipotential plane V equal to 0. Replace it with equipotential plane. Keep the rho L as it is. So rho L equal rho L at where is the location? 3 comma y comma 4 equal to 16 into 10 power 9 coulomb per meter. So exactly below at the same height you need to put the image. So what should be the value? It should be minus rho L, and the location, at least you say the location where it should be kept. See, this is z equal to 0. Guys, understand this is z equal to 0. Z equal to 0. So what should be the value here? Three comma y comma minus louder.
3 comma y comma minus 4.
Correct. Right. So it is 3y minus 4. Right, because the height above it's a 4, so below it should be minus 4. That's why. Okay. Now let us calculate the electric field. So total electric field is electric field due to the rho L and electric field due to minus rho L, which is on the bottom. If you recall, electric field due to infinite line charge, this from the second module, electric field due to infinite line charge is rho L 2 pi epsilon naught into rho, and it will be perpendicular to the radial direction. So this is a general formula for electric field due to infinite line charge. Now let us apply E vector is equal to, now let's write for the, okay, let us first write the general equation, rho L1 over 2 pi epsilon naught into rho 1 into for simplicity, now we take this rho L over 2 pi epsilon naught. You know, any vector is vector over its magnitude, right? So you can write like vector over its magnitude. So it will be rho square, right? Sorry, rho vector by rho square. Okay, so it will be rho 1 square into rp1 vector. Same way, the second charge rho L2 over 2 pi epsilon naught, the vector connecting the end observation point or field point and the source point, that is rp2 over its magnitude. Sorry, not p, it is rho. Okay, rho 2 square. Maybe you can take like its magnitude, right? You can even take r, no issues. Now write the equation for let us write the equation. This is what the critical thing. Not critical, simple. This is a simple thing. What is the unit vector equation for r rho 1? Give me the equation. Where is the field point? Where you are observing? That's here. You need to calculate electric field at, this is the first part of the question, electric field at 2 comma minus 2 comma 3. So this is the observation point. So that is the field point. You are observing at 2 comma minus 2 comma 3. Where is the source? Where is the source? Source is at 3 comma y comma 4. So it is 3 comma. What about y? Y should be minus 2. You should take the perpendicular distance. Minus 2 comma 4. Same way for the the vector which is connecting the observation point and this source. This source is this source. I'm talking about this source is observation point is at my 2 comma minus 2 comma 3, and where is the source? 3 comma minus 2 comma minus 4. That's all. I'll give 2 minute time. Please complete this. Now you need to take the magnitude of this. Then you need to square it. Don't forget, you need to square it. Any questions? Now, second part of the problem. Calculate the induced. I'll give 1 minute time. Please complete. Any questions?
No, sir.
Okay. Okay. Assume you have done okay with this. Now let us move to the second part of the problem. Second part of the problem, you need to calculate the charge induced on the surface. Because you are bringing a positive line charge above the metal plate, what will be the charge induced on the metal plate, that you need to calculate. So you need to calculate only the induced surface charge density. Only rho s you need to calculate. Okay. So rho s equal to dn, right? Dn equal to epsilon into En. Okay, so rho s equal to dn1 plus dn2. Guys, please understand. Look at this value where we were supposed to calculate 5 comma minus 6 comma 0. That point z is at 0 itself, right? So in order to force the condition z equal to 0, so usually it will be as you are asked to calculate the surface charge density, always this value will be at 0 only. Okay, so here z will be 0, then only you can we can specify the point on the surface. Okay, so it will be z equal to 0 only. So dn1 plus dn2. So now directly if I copy and paste, maybe you can do it, no issue, you can do it once again. So dn1 into dn2. Don't worry about this, you just directly put all those values, like now directly let me write rho l over 2 pi, right? That epsilon naught time will get cancelled, right? So what else will left? R vector, r1 vector by its magnitude minus r2 vector over its magnitude. Now question is what is r1 and r2? If you calculate that, it's okay. It's the problem is done. R1, R2. Can some of you say what is R1 and R2? So you can put R1, or if you want, you can detail write R row 1. I think R1 and R2 will make sense, right? So we can avoid writing like R row 1. Maybe you can replace it with R1. So what is R1 vector? Yeah, very same way you need to tell where you are calculating and where is the source. That's all. See, somebody is trying. So I'm giving the opportunity. If you don't want, I will share the answer. No issues. So it's endpoint minus starting point or field point minus source point. You want to calculate it? Yeah, louder, please.
1
Louder.
second, sir.
Yeah, take your time. No issue. Just to tell the point, that's sufficient. These are such a question where you can easily score. No integration, differentiation, divergence, curl, nothing is involved, but still it is electromagnetic subject. So likewise, you will get almost some 40 questions, 40 marks even in the FAT exam, where without any vector calculus, you can score.
Sir, 2 minus 4 and minus 4.
Okay, it's 2.
2 comma minus 4 minus.
No, don't tell the answer. I first tell the points, end point and starting point, R1 vector.
Endpoint will be 5 comma minus 6 comma 0
Yeah, that's
minus
what. Yeah. 0.
3 comma minus 2 comma 4.
Repeat.
So
Where is the
3
source? 3 comma.
comma minus 2 comma 4.
Minus 2 or minus 6. So what will be the y? The y value should be perpendicular to that line, right? See, that is the infinite line, and the observation point you are taking somewhere here. Let us say somewhere here. Okay, so the
Yes, sir.
observation.
Yes, sir.
Okay, so it should be minus 6. See, this is the most common point we will get one. Sorry, with this infinite line problem. So infinite line problem, to calculate the distance, radial distance, you need to replace this y with this value. Okay, so you need to be aware you are calculating a distance perpendicular from this point. Sorry, this point. So it's 3 minus 6 comma 4. Is it right? And then same way for R2, can you tell? R2?
So 5 comma minus 6 comma 0 minus 3 comma 6 comma 4.
Minus 3? Is it minus 3? Where is the source? X is equal to minus 3? You need to be careful about this. X is not minus 3. See, this is 3. See, that's why you are taking the mirror, right? If you are taking a mirror, only the Z value will be mirrored, right? Because
Yes,
it is
sir, I
Z
told
plane.
3, sir.
Oh, sorry. I thought it is plus minus 3. So it is 3. Repeat, 3 comma.
So minus 6 comma minus 4.
Yeah, exactly. That's all. Okay, so if you calculate, you will get this answer. Maybe you can cross check. So the point here to note down is this. I think you all comfortable with this calculations. This endpoint, starting point, these calculations you are comfortable with. But usually this will be at the z equal to 0. So ultimately the answer d vector will be some value. It should be perpendicular to the plane. It should be perpendicular to the plane. Okay, and in this case, this is a plane, and the rho L is at the top, and so it is like a positive, right? It is a positive charges, right? Then what is the direction of, what should be the direction of electric field? This should be the direction of electric field. Okay, so then it should be minus AZ, right? Guys, understand it is minus AZ. It is not plus AZ. Hope you know the reason. Minus plus rho L is there, and it is like negative rho L is there. So electric field lines will be in this direction. It will start from the plus and it terminate in the negative, right? So it should be in this direction, which is minus Z direction. So this way you can cross check your answer. Any questions? So you'll get similar problems, only this maybe these values will be different, or maybe instead of rho L, it may be rho S, or it may be rho V, that's all. So you should know, you need to recall the formula for electric field. See, for solving this particular topic, you need to recall electric field due to infinite line charge, infinite surface, or volume charge formulas from the from the second chapter. You need to refer the equation. Maybe point charge. Point charge you can easily recall, but for the surface charge and all, you need to recall the precise equation. If there is no questions, I will go back to today. I am completing this topic. We are winding up this boundary value problem topic. Boundary value problem. So far, we have solved some problems, some 2, 3. I think more than 3 problems based on the using Laplace and Poisson equation. And today we have solved. We have introduced with one new topic called method of images, which is a very simple method where we are replacing these boundaries, metals, and with the image of the charge, and with simple effort we have calculated electric field, potential, and the charge induced. All this we have done. Now I want to go back. I want to discuss this specific example. This is available in your textbook. Just I will give you some clue or the important points about this. The rest, as usual, this Laplace and Poisson calculation. You will take the equation, you need to integrate it twice, then you will get the voltage, then you can calculate electric field the same way. Now look at this, read the statement. There is a metal bar of conductivity sigma bent in the form of flat sector. So this is a metal bar with some finite conductivity. The inner radius is A, outer radius is B, all this stuff is given, and the thickness is T is the thickness. Now, we need to calculate the resistance. So resistance general formula is rho L over A, or you can say L over sigma into A. Here in this case, sigma is the conductivity, L is the length of the conductor, A is the cross section. You can use this formula only when the cross section is uniform. Only for the uniform cross section you can use this formula. You can use if the cross section of the conductor is not uniform, then you need to use this formula, R equal to V upon I, V equal to negative E dot dl, and I equal to Z dot ds, Z equal to sigma E dot ds. Then this is the only way. Okay, you have to use this formula if the cross section is non-uniform. This is the first point to understand. Now let us consider two problems in this regard. One is, first question is, what is the resistance between the two vertical curved surfaces? that is rho equal to A and rho equal to B. That means this is one curved surface. I'm shading with the black color, and other surface is rho equal to A. This is the other surface, rho equal to A and rho equal to B. So it's very clear that rho equal to A, rho equal to B, you are getting some surface, but they are of not of same uniform cross section. Rho equal to B is quite larger, bigger than rho equal to A, right? So you can't use this formula. You need to go with the equation 2. This is the only way, right? Is it clear? Now you can assume like this plate. This is like a plate. Black shade is a plate with V equal to 0. This red shade we can assume like V equal to V naught. Or if you want, you can in other way also you can take, no issue. The answer will be anyhow, it will be same, no issues. Okay, this is the one question, first question. Now second question, read the statement clearly. What is the resistance between the two horizontal surfaces? Earlier we took two vertical surface, now it is horizontal surface. Now I will clean this page, otherwise it's difficult for me to highlight. Two horizontal surface, one is Z equal to 0 and Z equal to T. What is the resistance between these two surfaces? Where is Z equal to 0? Z equal to 0 is this bottom plane, this one. Z equal to 0. Z equal to T is the top, I will use black color to highlight. So this one. Right? Otherwise, I will enlarge this picture, otherwise it's difficult for you to see the second question, second part of the question, you need to calculate the resistance between Z equal to 0. This lower plane is Z equal to 0 and this is equal to Z equal to T. Now which formula you will use? Whether the cross section is same or cross section is different. Z equal to 0, that metal, the blue region or the sector metal is same that of Z equal to T, right? Both are same. Area is same, cross section is same. So as the cross section is same, you can use this formula, R equal to rho L over A. Sigma is the conductivity. L, this, what is the length here in this picture? As from this picture, what is the length? What will be the numerator? What will be the numerator? What is the length of the conductor that you're supposed to consider? Right, we are measuring the resistance between Z equal to 0 and Z equal to T. Then in this case, what is L? Length of the conductor. This is will be the length. T is will be the length. And sigma into A. A is the area of this region. You can calculate the area by using this formula. Right, like you can use the cylindrical coordinate system and you can calculate. That's all. So the solution is available in the textbook. The slide also I will upload. If any questions, you can maybe you can ask it. Maybe you can clarify in the next class. Any questions related to this question?
What was the area?
Yeah, area. You need to find this area. Yeah, this area you need to calculate. So it is like rho is from A to B. Right? Rho is from A to B. And what about theta? What about theta and what about phi? So what is the surface area equation? First, let me tell. Let you tell. Can you tell this equation for ds? Surface area equation for cylindrical coordinate system. See, the surface is perpendicular to z direction. Correct. So what are the things varying? Radius is varying. So d rho and phi is also varying. So rho into d phi. So you need to integrate this. Now the question is, what is the integral limit? Rho is from A to B. Phi. What about phi? What about phi? Come on, try. Sorry, theta is not applicable here, right? Yeah, this is cylindrical coordinate system. What about phi? Here it is 5 equal to 0. Yeah, 0 to?
Pi by 2.
Exactly correct. 0 to 5 by 2. Okay, so maybe in the exam I can make it like I will put it like this. Okay, from up to 5 by maybe 5. Okay, this is what I can expect. Okay, so similar questions, but geometry, little modification in the geometry or some other kind of geometry I can show. Okay, but ultimately the idea will be same, the concept will be same. So with this whatever clue I have discussed now, you directly take this problem available in your textbook, try it in your own, calculate this resistance value for both cases. If you can able to do it in your own without you can able to do it in your own, then 10 mark is assured in this CAT exam. Any more questions? Thanks for joining. You may leave now if there is no questions with you.